Hi, everyone. My name is Danny Vainstein, and our paper is titled Hierarchical Clustering, a 0.585 Revenue Approximation. And this is joint work with Noga, Alon, and Yossi, Azar. So we'll start with a simple example. Assume we have a set of data points. These are represented in the green circles. And assume we have some notion of similarity between them. So between every two data points, we have an edge with a weight. And this weight represents how similar the data points are. So the higher the weight, the more similar the data points. Many times we'd like to cluster the data points into sets such that data points within the same set are more similar to each other than to others. So in this instance, we can see that these two data points are much more similar to each other than the others, and the data points within these four are also much more similar to each other than to the other two. So an intuitive clustering would be this one. Many times the resulting clusters are fairly large, and this fails to capture the relations between the data points within a given set. In order to overcome this, an idea is to further cluster the sets into smaller clusterings. So in this case, we can see that, for example, these four nodes, the top pair and the bottom pair are much more similar to each other than the rest, right? So an intuitive clustering here would be simply to cluster like that. So this results in a hierarchy of clusterings, right? Another way to view this hierarchy is as follows. First, we place the data points on the bottom, and then we build a tree above the data points. So the tree is basically a tree, and the data points are the leaves in the tree. And this tree represents the hierarchy clustering as defined before. Why? Well, basically, every internal node can represent a cut or a set or a cluster, of the data points, like so. So for example, this red internal node represents this cluster, and the entire tree represents the hierarchy of clustering. And this we call the hierarchy clustering tree. So now that we defined what a hierarchy clustering tree is, or HC tree for short, a natural question would be to understand what a good HC tree is. So before we try to answer this question, first let's introduce some notations. So our problem is formally defined as follows. We're given a graph with edges and weights on the edges. The nodes of the graph represent the data points, and the weights on the edges represent the similarity between the data points. And our goal is basically to construct an HC tree such that the leaves correspond to the data points, right? Like the example we saw. And throughout this talk, we'll denote by Tij the subtree that is rooted at the LCA of I and J for any two data points I and J, and given an HC tree T. And the size of Tij is not the size of the subtree, but rather the size of the number of data, but actually it's the number of data points inside the subtree Tij. So in 2017, Mosley and Wang defined the revenue goal function to be the following. First of all, you try to maximize this value over all of the HC trees. And this value is defined as follows. First of all, we sum over all pairs of data points I and J. And for every pair, we look at the value Wij times n, which is the overall number of data points, minus the size of Tij. So basically, this is the number of leaves outside of Tij. All right, so let's see an example. So here we're given an HC tree and two data points I and J with a similarity weight of 350 between them. So in this case, the size of Tij is 2, right? Because there are two data points within this subtree. On the other hand, we're interested in the number of leaves outside of Tij. So in this case, you can see that it's 5. And then towards the revenue, we count the multiplication of Wij times n minus Tij. So in this case, it's 350 times 5. And this is intuitive in the sense that we'd like data points that are more similar together to be clustered lower in the tree. So we'd actually, given ij, we'd like to minimize the size of the subtree that contains it. So instead of minimization, we were looking at the maximization variant, which is to maximize the number of leaves outside. And then the revenue is defined as the sum of all pairs I and j. All right. So a little bit about former results. So Mosley and Wang looked at both the algorithms of average linkage and random. Average linkage is a bottom-up algorithm that is used many times in practice, where at each point the algorithm takes the two clusters that maximize the average linkage between them, which is basically the average weight between the two clusters, and then it merges those two clusters and continues iteratively. The random algorithm is a top-down algorithm where at each point it takes a set and splits it randomly into two sets, thereby creating the HC tree. And Mosley and Wang showed that both of these algorithms are a third approximation. Later, Hierarchical et al. Showed that actually you can beat these algorithms, and they showed through the use of semi-definite programming a 0.3364 approximation. Even later, Ahmadian et al. Showed a 0.4246 approximation using the max uncut bisection algorithm together with the random algorithm. So a little bit about our results. First, we showed a 0.585 approximation. I'll talk a bit about the algorithm a little later. But to show this theorem, we actually proved a different theorem, a structural theorem, in the sense that it doesn't provide a polynomial time algorithm, but rather it just shows an existence of something. And the theorem is as follows. We show that there exists an uncut bisection that generates half of the optimal revenue. All right, so what do I mean by an uncut bisection that generates revenue? So here's an example. The revenue goal function can actually be viewed as follows. Instead of summing over all pairs of data points I and j, we can instead sum over all internal nodes, or all of the cuts in the HC tree. So for example, consider the root. This cuts V1 through V4 from V5 through V7. So we'll denote the left-hand side as the set A and the right-hand side as the set B. And we denote by WA all the weights within the set A, and WB all the weights within the set B. Right? Then we say that the revenue generated by this cut is actually this value, which is basically taking the weights within B times the size of A, which in this case is n-3 because there are only 3 leaves in B. Okay, plus the corresponding value, which is WA times the number of nodes in B, which is n-4 in this case. And it's pretty clear that that if you sum up over these values for every cut in the tree, you get the revenue of the HC tree. So basically, when we say that there exists an uncut bisection, we actually mean that there's a tree, and within that tree there is a cut that is actually a bisection, and that cut generates revenue that is equal to at least half of the optimal revenue generated by the optimal tree. Okay, so now I'll quickly go over how we generate this bisection, or how we construct this bisection. In the paper, we prove that it's actually a half approximation, but I won't have time to get into that. Okay, so as a first step, we first of all look at the optimal tree. All right, so assume we're given the optimal tree. Remember that this is a structural lemma, so we in fact can assume that this is an optimal tree. So first of all, we take the optimal tree and we fix or embed the leaves on a line. So in this case, let's assume that the leaves are V1 through V6, and their embedding on the line is actually V1 through V6. So a small note, the placement of these leaves on the line isn't unique given an optimal tree. So for example, you could take the optimal tree, look at this internal blue internal node, and swap its left and right subtrees. All right, and this would give you this placement on a line. So given an optimal tree, we can see that there are actually several placements on a line, or embeddings on a line. So our first step in constructing the bisection is to pick such an embedding randomly and uniformly. Okay, so now we have this embedding on the line. So the next step, we randomly pick one of the n/2 leftmost leaves. So in our example, we look at V1 through V3 and pick just a random leaf from these. Okay, let's say that it's V2. The third step, we then take an interval size n/2 that begins at V2. So in our case, this will be V2, V3, V4. So basically, it's an interval of size 3 that begins with V2 and goes to the right. Okay. Now, as a fourth step, we bisect. Okay. What do I mean by bisect? We take the 3 chosen nodes, or the n/2 chosen leaves, and cut them from all the rest. So we generate a first cut, all right, like so. And notice that this is actually a bisection, all right. And now we simply continue generating an HC tree arbitrarily, okay. So our theorem states that given the optimal revenue tree and the revenue it generates, actually this bisection, the first cut in and of itself, already generates a revenue that is half of the optimal revenue. And note that by the definition of the revenue a cut generates, it doesn't really matter how we continued building the tree. Okay, any tree that we build after this bisection doesn't impact the revenue generated by this bisection. Furthermore, we don't actually count any of the revenue generated within the rest of the tree, but only the revenue generated from this cut. And already that is enough to yield half of the optimal revenue. Okay, so now the next theorem is the algorithm, the 0.585 approximation. So the algorithm is as follows. For the first step, we generate a bisection by using a black box approximation for the max uncut bisection problem, which is basically a bisection that maximizes the uncut edges. All right, so now we have our first bisection. Thereafter, we just continue cutting each set randomly, all right, using the random algorithm. So now that we define the algorithm, basically the revenue generated is, so let's say that P is the approximation for the max uncut bisection problem that we get from using the black box algorithm. So in this case, the revenue generated is P/2 plus P/6, where the P/2 is the revenue generated through the first cut, and this analysis relies on our structural theorem. And then the P/6 is basically all the rest of the revenue that we get from the random algorithm. And it is known that P is at least 0.8776, and for this value of P, we get a 0.585 approximation. All right. So just to conclude, our results are as follows. First, we showed so the first theorem is a 0.585 approximation, and the second is a structural theorem that states that there exists an uncut bisection that generates half of the optimal revenue. And just a small note, this structural theorem is tight in the sense that there exist instances where this is the most you can hope for. Okay. So a little bit about open questions. We would be really interested to see this embedding technique used in other models. So for example, one could look at the dissimilarity model defined by Cohen et al. And try to use this embedding technique in order to get better results there. And another question is hardness. Whether we could hope for anything much better than 0.585, or whether there's some inherent difficulty in improving upon this result. That's it. Thank you.